Hi and welcome back. What we're going to do now is we're going to get down to business, I guess, for the first sort of real coverage of material. So the first thing I want to do is give you a heads up about one of the key pieces of software that you're going to use, which is a software called R. Now R is open source, which means it's free. And if you're interested in becoming a scientist or doing some work, one of the great things about this is it means that you can share on a common platform and your research can be reproducible. And that's a really important thing. The other thing that it means is that when you get a job and you need to do some analysis, you don't have to go to your boss and say, can you buy me, at uni I had software, I had GenStat, or I had Gauss, or I had Stata. I had one of these things that cost thousands of dollars. Can you buy it for me so I can answer the question that you've asked me to? You don't need to do that. You can use R, which is the open source free platform, and it's the cutting edge platform. Now, the downside to this is that there's quite a steep learning curve, and I'm not I'm not understating or underselling you or overselling you, I guess, when I say that I have genuine faith in you and your ability to be able to pick this up. On average, the cohort that comes into the class is pretty bright. And it's challenging to learn this stuff, but I find that people really are up for the challenge. So many people would say that it's too hard to set first year's non-GUI based statistics. I disagree. My experience is that if you provide a supportive learning environment, students are up for the challenge. And I really think that you will learn a lot, and you'll have some frustrating moments, but you'll be on the path to success. And I think that it's really important that we get you on that path from the start. The other one that we're going to learn a little bit about is Excel, and Excel is ubiquitous. It's in every workplace, and so it's good for us to get some skills, and it's really good for data management. You can't do statistics with Excel. The options available are very, very limited, and so really not worth learning. So we're going to stick with R for graphics and some of our statistics, and Excel for data management and creating tables and those kinds of things. Now, what does the R look like and how different is it to Excel? So the version on my computer is a little bit different from the one on the labs. Well, only in terms of the addition, it will look exactly the same. So I just kind of had liked they all have different names for each version, and 3.30 was supposedly educational, and of course, for me that was kind of a bit funny, and so I've kept that. But we've updated the ones in the computer lab, but the look is exactly the same. So what I guess I thought I'd show you is something simple that you would do in Excel, or you might be familiar with in Excel, and how it would look in R if you had to do it in R. And it's really just creating a bar chart. So if we had something like a bar chart, so there are some rules for bar charts. We like them to be ordered from highest to lowest. We like them to be nice and clean, nothing fancy, and the largest column shows us the priority area. Now, if you were wanting to create that in Excel, again, I have a pretty dated version of Excel on my computer, but I would go to the bar chart column, I would select the data that I've typed into Excel, I would select the kind of column that I want. The default would give me something, a bit ugly like this, and then I would start editing my picture to make it look back like this guy. All right, so we know this, yes, we're pretty familiar with this kind of stuff in Excel, and we're pretty familiar with this kind of screen. If we wanted to create this in Excel, it's the same but different, if that makes any sense. So let's have a look. So we need to enter the data. So just like we typed in the numbers in Excel, we type in the numbers in R, but we would call them an object. So we just have to give them a name, but there's nothing really different to what you would have done in Excel. And then just like we typed in the group names in Excel, we type in the group names in R, but we call them the names, and these are the names that apply to the object waste data. And then we just press we have to type in the function box plot. So we selected the bar chart. We selected the bar chart in Excel. If we just select the bar chart in R, which we do by typing in the word bar chart, we get the output that we want. So it would be bar plot around the values that we want the bar plot for, and we get a bar plot. So that's very much, pretty similar to what you would do in Excel. There's just typing instead of clicking on a menu. So it is a little bit different, but once you get the hang of it, it's not too much of a problem. Now, I want to emphasize, if that seemed a little bit crazy to you, or a little bit you're thinking, oh goodness, I'm feeling pretty unsure about this unit now, don't worry. Why? Because we have this sort of very structured approach. So the first lab that you do, it's sort of completely 100% guidance. You just sort of click through things and you can see how it works, and it's a completely worked example. And then you'll do some trial exercises on it, and then you do your own work on it. So you'll have sort of an example, and then you'll have to do your own repeat. So it's a very, very structured learning process. So don't worry about thinking, oh, I'm not capable of doing that. Oh, that seems all a bit crazy. We've got lots of support for you. We've also got some reference guides for you. So I'm going to split these out into 2 lots for you over the semester. The first lot, I'm going to do things where you'll get, a very, very specific guide. So in a lab where we're going to have histograms, I'm going to have a document there just with the histogram stuff. But then you also have this comprehensive intro to R and complete resource. So you can see here the indexing of this. So you just download the PDF. You've got all of this documentation. You can open each of those tabs. They're indexed. It's a completely indexed operation. So all of those individual chapters are there sitting in a nice book for you. So you have a comprehensive guide to how to do this, a comprehensive guide to introductory statistics. And it's free, so it was a lot of work. Hope you find it some value. If you find mistakes, please let me know. It's my first edition of putting this together, so I'm sure there are many mistakes. So please let me know and I'll correct them for students in the future. Now, a lot of this presentation material, or the stuff we goes towards presentation, and just I'm going to have a brief segue into a couple of things about good and bad plots and some examples. We'll see a number of examples on how we go. For plots, there are a couple of rules that we're going to have for the unit, and there is a detailed guide on what the rules are. Caption labels can be above or below the picture. That's going to be okay. But we really want to have some level of customization. Tables, caption labels are going to be above, and we're never going to be able to see the grid lines, and we want to remove excess zeros or scale our data in some way. And I guess what I'm going to illustrate is just some shots from some papers that have been around. So I just thought here was an example of something that had set the plot space nicely with above and below line, and it has the figure caption above the picture. So some journals have figure captions above the picture, some below. Here's another one that had the figure caption was below, so that's why I'm going to be accepting figure captions above or below. Both are in works that I've seen. And here's one where I also saw, so this one is below, but it's a fig reference. So I'm going to also accept, fig.1 in your setup. So these are just examples that I had lying around of things that have been published, and you can see that there's a wide variation for tables. For figures. For tables, I just thought I'd highlight something that I want us to avoid. So I recently refereed a paper, and this was the table that I got, and I couldn't believe this. So this is some regression results table. And look at the ones that I've highlighted there. I mean, they're giving me a table where the value is 0,0,0,0,0. And how am I meant to interpret that? I just thought, this is bizarre. You've just filled out this table without even thinking about what you're doing. So we're not going to be doing that. So I thought, well, let's just get on the right foot straight away with this. So I just thought, here's an example of something that's formatted very badly. And here's something where I've tried to clean it up a bit. I'm not saying that these are, the worst and the best, but just showing like there are obvious mistakes here. So we never have grid lines when we present a table. If we're going to have New South Wales, the S and the W should be capitalized. The values should be aligned. So you can see that mean is hanging off to the left, and then the values are to the right. You can also say this is measuring in units of millions and it's got 2 decimal places. I mean, come on, who needs decimal places when we've got millions? And so just I've taken that same data and just cleaned it up a little bit in the table, in table 1, just to say that looks, it's now clear. The values are grouped with New South Wales and with WA. It's the mean and the standard deviation, which are the things that we're often interested in. And it's been, the data's been transformed to be expressed in millions. So, we just want to avoid bad looking tables, I guess. So now we're going to look at some key concepts. And again, this is just some revision for you. I'm pretty sure it's going to be some revision for you. I'm just going to recall a few things that you may have forgotten since you did your last course on something quantitative. So just with the mean is the first thing that we're going to start. Okay, it's traditional to use the mean to describe the center of a distribution, and we're often going to be doing that. So just reminding ourselves, we're going to be using Excel to calculate means. So really we just need to be aware of the formula in Excel, which I'm sure many of you are already aware of, which is just the average, and you select the cells that you want to calculate the mean for. And if we wanted to write in formal notation, we would write the sum of the xi divided by n, which just means add up all the values in our sample and divide by the number of observations that we have, and that's the average. So we all know the mean. The other thing that we usually pair with the mean is the standard deviation, or in particular the sample standard deviation. So the reason that we tend to have the mean and the standard deviation together is particularly for symmetric distributions, that if we know the mean, we have these sort of decision rules. About 2/3 to 70% of the data are within 1 standard deviation of the mean. 95% of the data are within 2 standard deviations of the mean, and almost all of the observations are within 3 standard deviations of the mean. So if we know the mean and we know the standard deviation, we kind of know where all the data points are. And so those 2 numbers give us a very good description. So as scientists, it's easy for us to just look at 2 numbers and say, okay, we know, what's going on with that distribution. So if we were to calculate the sample standard deviation in Excel, we would use the stdev.s formula. So we always use the .s because we'll always be working with samples, not populations. And if we look at the formula is this expression down here, which says in words, take sum up, or the squared differences. So the xi index is the individual observations, the x bar is the mean. So sum up the squared differences, divide through by the sample minus 1, and take the square root of that. So if we want to get a measure of what the standard deviation is, rather than paying too much attention to the formula, it's helpful for us to know what's driving the results. So if we just look at the formula, what you'll see is that we've got this bit sitting at the top. So this is the sum of the squared terms, right? So what this tells us is there's lots of spread in the data. So the individual observations are spread far around the mean. Then that value in the numerator, when you add up all those differences, is going to be large. And if that's large, then the whole result will be large. The opposite is also true. If all of the little xi's are quite close to the mean, then the numerator will be small, and then at the end of the day, everything will be small. So if we've got large spread in the data, so the observations are widely spread, we'll have a large standard deviation, and if the values are clustered close to the mean, we'll have a small standard deviation. Okay, and now let's just look at a sample calculation to get this clear and reinforced in our mind. So I have my sample set of numbers, which is the same set I used for calculating the mean. I calculate the mean, so that's my x bar, no problem with that. I calculate all the squared distances. So I'd have 4, the first value minus the mean, the second value minus the mean, and I square them all. So then when I square all of those, the negatives and the positives all become positive, and I end up with 18.9. So I've got my sum of squared differences now, and then if I look at my formula, I need to divide through by the square root of the sample size minus 1. So if I do all that, I end up with 1.54. So we've got the mean and we've got the standard deviation, and we use that to describe the distribution. Remember, mean is where the middle is, and or the weight of the probability density, and the standard deviation, the spread. So one standard deviation somewhere usually picks up somewhere between 2/3 and 70% of the data. Two standard deviations around the mean is going to pick up about 95% of the data. So if we were looking at, why would we want these sort of values, and how do we use them, or how do we sort of, calculate tables and present this sort of information? Sort of an example that we might consider here is something to do in the biodiversity context in the southwest. So we have some marine issues here, a particular type of marine that we might be looking at here. So restocking issues, how are the waterway health? What are we doing in there? And so we might have a data set, some restocking experiment on what we're doing, or we want to take pressure off the wild marine and we want to have farmed marine. So we want to say, look, we're going to stop people taking the native marine, and we're going to let the ecosystem recover, and we're going to grow some marine in some ponds that we can farm. So we might have a bunch of measurements, and the kind of scenario I'm imagining is something like this. So we have a data set where we have different sort of measurements. So you can see I've got 6 different strains of marine. I've got male and female marine, and I've got measurements on the tail flesh. And in this context, the tail flesh is what we're going to sell. So that's something that we're interested in. So we would have these sort of groupings. So we've got tail flesh by strain, by the sex groups. So there are a number of different subgroups, and we would probably like to calculate the mean and the standard deviation for each subgroup. So that would be able to tell us, which groups are, on average bigger. Are males bigger than females? In this, generally the story there is yes, but which strain is having more tail flesh than others? So if we had the mean and the standard deviation, we would be able to have some information on that. So the way that this data might look in Excel is something like this. And so here I've just trimmed off, you can see the start and you can see the end observation. So you can see that the way the data is represented in here, and we have different types of data. So for the tail flesh body weight and a carapace width measurement, we would say these are continuous variables. They can take on a wide range of values. The same for the tail length. But for sex and strain, we would call these factor variables. And then these are categorical variables. They're not numerical. So the language we use in science is we tend to call them factor variables. And with the number of different categories we tend to describe as the levels. So for the sex variable, we have 2 levels. The levels are male and female. And for the strain, we actually have 6. Okay, we know there are 6 because we saw that earlier over here. You can't actually see the full 6 on this, but you can see that the observations run to 234, and I've hidden from observation 5 to observation 246 the strain or all of the information, so you can't see the strain. So we have 6 strains. Now the way that we would calculate the mean and the standard deviation for this is we would use in Excel what's called a pivot table. So a pivot table is going to be something that allows us to do the grouping. So we're going to be able to group by factor, and then we're going to be able to get the mean and the standard deviation. So we would be able to calculate very, very quickly the subgroup. So just knowing our average and standard deviation formula is not going to help us that much, because we need to be able to do them by the subgroups. And we want to be able to do that quickly, efficiently, because that's one of the core things that we use to describe in science. We're often doing that. So we want to describe all of those things, and that's going to be the topic in the computer lab. And it's time for a break. Thank you. Bye.